Great breakthrough. So you'll, for those of you who are willing, you can suffer not only today, but tomorrow.
Okay, thanks. Wow, it's so nice to be here, and I'm surprised to see so many people in person. It's very awesome. Weizmann, Alex Lubotsky, and Shachar Moses. Okay, let's begin. It's just a linear subspace, so I'm thinking of like a field with two elements. The standard things we always have, and by the ambient dimension, and distance is the weight of the smallest weight code. Maybe it's less than. What is a locally tested? It's a code that also has a tester, but it randomly selects just a few bits of the word to read. So a few bits here is Q, and based on reading these bits, it says yes or no, accept or reject, and it has the following two properties. If the word is in the code, it accepts always. If the word is not in the code, then it rejects with probability proportional to the distance from the code. We can't expect it to reject with probability 2/3 because maybe only one bit of the code will be flipped, and you're only reading a constant number of bits. So the best we can hope for is to reject with probability proportional to how many bits were corrupted. Okay, so that's the notion of locally testable code.
So the distance is normalized, it's divided by n, or?
Yeah, I'm going to normalize both the distance, the rate, yeah, normalized between 0 and 1.
I can hide that. Sorry.
Good. And the locality is the word we use for how many bits from the code were the tester read. So it's the letter Q here. Is the
Sorry.
Okay.
Is there an arrow over
Oh,
on that
it's still
screen?
not.
Just the arrow. Sorry.
You can just get out of the.
I'm going to stop sharing it here.
I'll talk in the meantime. Error correcting codes, we know about them since 1948, since Shannon in his famous paper talked about them, and a random matrix gives you a good error correcting code with positive rate and distance. However, a random matrix will not give you a locally testable code. So this is not a notion that you would come up with, because it's very strange to expect to check that something by only reading a constant number of bits.
To check that something is in a linear subspace.
Right, because a linear subspace is defined by some constraints that are involve maybe a linear number of bits. So how can you expect that? But kind of this whole PCP line of work that started in the, I guess, early 90s or even before that in computational complexity showed us that things that are very complicated, like NP languages, can actually be checked by a constant number of bits. So you can conceive of this idea.
Sorry. So just try clicking on the screen with your mouse, and then you should be able to get full control over it.
When you say constant number of bits, you mean you fix the bits which you check, or you just fix the number of bits you check, but you can check each time different bits?
The second, right. Otherwise, if you always check these bits, then what's going on with the rest of the word? So it's really, what you have is a distribution over Q tuples.
And is it random? The way that you check, the way that you choose which
yeah, exactly. Right. So it's random. So this tester, what you should think about, you just have a distribution over Q tuples, and the tester selects a Q tuple from this distribution and reads these bits from the code word and then says yes or no. And you want that the fraction of times you say no is proportional to the distance from the code word.
It's totally independent. You don't necessarily choose the Q bits. It's completely independent of each other.
Right. It's not like you choose the first bit randomly and then independently choose another bit a few times. You choose Q tuples in some correlated way.
You have a distribution over the space of Q tuples.
Right.
It's not a product distribution.
Exactly. Right. Okay. So as I hinted, the way LTCs came about was first through works on probabilistically checkable proofs. And they were implicit in early PCP works. When you construct PCPs, you naturally want to encode the proof in some other way that's locally checkable. And the way it appeared in these works was under the name low degree test. We always use polynomial codes like Reed-Muller codes, or these are codes whose code words are low degree polynomial functions. And then what you wanted to check is that the prover is giving to you some low degree function, and this was called a low degree test. So this was really an important, a key component in construction of PCPs. And today, or many years ago already, in retrospect, you can think of this as showing that these polynomial codes are locally testable codes. So this is how this notion came about. Dan Spielman in his PhD thesis talked both about expander codes, which I'll show you soon, and also about PCPs. And he writes about the idea of having a code that's locally testable. He calls it, the local test he calls a checker. And he writes this, he says, a checker would be able to read only a constant number of bits from the received signal. This is the code word, or the corrupt code word. And then estimate the chance that the decoder will be able to correct the errors. Then the checker can instantly request a retransmission of that block before the decoder has wasted its time trying to decode the message. Okay, so that seems like a very useful thing. And then he adds, unfortunately, all known codes with local checkers have rate approaching 0, and in coding theory, this is considered not feasible to implement. So it would be nice to have something with constant rate. And okay. So it took another few years until Goldreich and Sudan kind of put forth this object, locally testable code, as an object worthy of its own study. And so they also asked, what's the best rate you can get? And then there ensued a kind of a thread of works trying to use technology that comes from PCPs to construct better and better codes. And all of these works came hand in hand. You constructed a more efficient code and a more efficient PCP, and then a more efficient code and a more efficient PCP. And kind of the best state of the art was a rate that's 1 over polylog. So it goes to 0, but it's not so bad. Okay. And then there was this notion of C3 LTCs, so constant rate, constant distance, and constant locality. And the question is, does such an object exist? And people were not sure. People doubted it, and some people, including myself, tried to prove lower bounds for these objects, tried to show that if you want this local testability, you must pay a price. There must be so much redundancy that the rate cannot be too good. And okay, there are some works, but always they were restricted. So we didn't manage to get good lower bounds.
So when you say constant rate, constant distance, it's you're taking a family of growing linear subspaces, and
Right.
once that these 3 parameters are fixed.
Exactly, yeah, exactly. So you think of the n, what's called the block length of the error correcting code is going to infinity, and the rate, distance, locality are fixed to be something.
And locality would be the number of bits normalized in some way?
No, it's not normalized, that's the point, it's a constant. So you read 100 bits, the length goes to infinity, 100 stays 100.
Oh, I see.
Like the degree of an expander.
But the success rate is dependent on the distance, right? It's when your success is normalized in distance, but the distance is constant. No, I'm sorry. It's the difference. The distance of the input from the code.
The distance of the code is a constant, but the distance of, but what you need to achieve is that if you're given a word, you measure the distance of the word from the code, and the fraction of, or the probability of rejection should be proportional. So if it's very close to the code, you shouldn't reject too much. Yeah.
If there is a constant function of errors, you should detect it with constant probability. That's really the.
Right. Okay. By the way, for PCPs, we know like these excellent PCPs where you only need to read 3 bits in the proof. The thing goes to infinity, but the number of bits is only 3, so it's quite unbelievable. It used to be unbelievable, now we got used to it. Okay, so these were, okay, we were here, and then I want to say, on the flip side, you can ask, okay, suppose I force the rate to be constant. Let me try to see what's the best code I can get. And people managed to get locality that's pretty small, like almost polylog n. And this is already departing from PCP constructions and just trying to construct codes and use expanders in clever ways and so on. Okay, then other works were interested in trying to understand what makes a code testable or other properties testable, and trying to understand this notion of local testability, it's a kind of robustness, what makes it work. So affine invariance turned out to be a very important property of all these polynomial codes that allows for local testing, but we didn't know really, other than all these polynomial codes, we didn't really have almost any other example of locally testable code. So it's a bit hard to understand what is the inherent thing that causes this thing to work if you only have one family of examples. And then came this, suddenly this idea of high-dimensional expansion, which is a completely different notion, completely different family of objects. And it looked like, oh, wow, this can maybe also lead to local testability. And this is a very different thing. So once you have, if you manage to get two families that give you the same property, it really, I don't know, it broadens your perspective in some way. So Lubotsky and Kaufman were the first ones to notice that these high-dimensional expanders give you property testing of a certain kind. And kind of this opened the door to saying, oh, well, maybe we can use these things to construct locally testable code. So let's see.
You did mention that property testing is the mother field in which local testing of codes is a special case.
Okay, thanks. Yeah, so kind of, I said we started with working on PCPs, and then from the ideas of PCPs, this whole field of property testing was developed, kind of in parallel to this idea of locally testable codes. It's like a special case of property testing.
Property testing is the same as with the code, but you want to test other properties, not that you are close to a code, but that you are close to a bipartite graph, or you are close to a monotone sequence, or things of this type, just by randomly sampling a small piece of the input.
Right, but in property testing.
In general, I should mention the seminar we ran last year here about stability in group theory, which can be really taught as this type of question in the theory of groups, this kind of question, whether, say, permutations or matrices satisfy some property, commutativity, etc., can be thought of as a non-commutative code. So it can, like almost homomorphism, the whole theory over there can be put also into this framework.
Right, so one thing though to distinguish between these notions, in property testing, for example, graph property testing, you want to know whether some graph property is testable. If I get a graph, can I test if it's close to being a three-colorable graph? That's a property testing. In this area, the property is given to you, it's some natural thing, like a graph being three-colorable. You're not going to engineer the property to make it property testable. Okay? It's given to you and you need to see what's the best you can do. Whereas here in codes, you get to engineer the code and then you get to try to prove if it's locally testable or not. And this also goes into these works. The kind of local testability that we get from high-dimensional expansion is like the properties defined by the object, whatever it is, I'm not going to go into it, these are locally testable. If you want something else, then it's not clear. Okay, maybe it's not so important now. Okay, so just to summarize this, so we really, a lot of people were thinking about this and we thought that high-dimensional expanders and codes can kind of be combined, and we even had a summer program in Berkeley at the Simons Institute, and you see the graphic designer helped us to show this, that you have some underlying high-dimensional expander, and on it you have the bits. So that's kind of the hope that we had. And so the main result I'm talking about today is this result for any rate, of course less than 1, there exists some delta in Q and an explicit construction of a family of aircraft encodes with these parameters. And okay, I haven't checked all the details, but I think it's also true that from previous works of Gopi et al., once you have that, and there's a transformation to also allow R and delta to be as close as you want to some bound that is the Gilbert-Rorschach bound, which means okay, these are very codes that are close to the best codes we know.
What about the alphabet here?
No. There was no existence known. That's a great question. As I said before, random codes are not going to be locally testable. Yeah, we didn't know whether these exist. And also a lot of people went back and forth conjecturing whether they can exist, cannot exist, unclear.
So some of the restricted lower bounds before were for symmetrical, it's like cyclic, right?
Right.
Is this called symmetric under some group?
Maybe. So you'll see. Alex doesn't
The
think so.
one which we have now,
They're not symmetric?
because we killed the action from both sides. It's like a
Oh,
Schreier graph, it's like the
I
difference
see.
between a Cayley graph and a Schreier.
It's a Cayley graph, but you're
It's a
left
Schreier
and
graph.
right, so you cannot act on the right and you cannot act on the
It
left.
can't be a cyclic code, for example.
Well, we also have lower bounds for
No,
that.
cyclic load, it's known, cannot even be LDPS, LDPC.
Yeah, there's work of Spilka,
Stefankovich and Babay.
Bye-bye, yeah, each other. Okay, so what are we going to talk about? So I want to start talking about expander codes. These are the famous codes of Sitzer and Spielman that should be viewed as like the underlying theme for this construction. Then I want to talk about a new kind of graph. It's not, okay, it's a graph, but has a second layer, like two-dimensional faces that are squares. Then we were going to define the code on this thing and maybe analyze some of the properties, or maybe probably most of the proof we will do tomorrow.
Is it's binary codes?
Okay, so let's start with the LDPC code. LDPC stands for low density parity check. This is when you think of a code as you take a random matrix and you look at the kernel of this matrix, that's your code. So Shannon showed that a random matrix gives rise to a good, the kernel is a good code. And Gallagher showed that the same thing is true for a random sparse matrix. And the way it's convenient for me to look at the matrix is you draw it as a bipartite graph, and you put an edge if you put an edge between I and j if the ij entering the matrix is 1.
So I are the bits of the codes, and these n bits satisfy some constraints, and they are given by the neighboring vertices.
Right. So you put the code word here, like the zeros and ones, and then this constraint checks that whatever it's seeing sums up to 0. It's a parity constraint. And I wrote it out here. You see, the words in the code are just n-bit strings. So this is n vertices, and for every vertex on the right, you have a constraint that says the summation of wi, all the neighbors, is 0 mod 2. So that's a definition of a linear subspace. And Gallagher proved that just like Shannon, it gets roughly the same rate and distance. But the benefit of looking at sparse matrices is that now you can decode. And he showed kind of the iterative algorithms for decoding, and that was considered a serious progress because the random matrix codes of Shannon, you cannot algorithmically decode.
The random here, random means a matrix, an n by m matrix of 0 ones.
Right.
It's random over the space of all.
Yeah, that was Shannon, and for Gallagher, it was an n by m matrix, but sparse, so that every row has a certain number of ones. Think of it as a random graph.
Yeah.
It's so that every vertex here has exactly the neighbor. Okay, so Tanner, 15 years later, or maybe a bit more, said, okay, I can generalize this a bit more, and instead of asking every vertex on the right to just check that the sum is 0, I'm going to choose some base code, C0, and it's going to be on d bits. So suppose that the graph is d-regular from right to left, and every vertex will just look at its neighbors and want that the string that it sees d bits. These d bits should be in C0 in the base code. And what he showed is that a lot of the codes we already know, like tensor codes, and he suggested some other codes, are already of this form. Gallery codes are, of course, a special case, but this seems to be a broader family. So to construct a Tanner code, you really need two ingredients. You need to tell me what the bipartite graph is, the factor graph, and you need to tell me what the C0 is. Okay, so our codes are also going to be Tanner codes. Okay. So move another 15 years forward, Sipser and Spielman came up with a concrete suggestion for a Tanner code. They said, let's choose the factor graph to come from an expander graph. So I'll show it in the next slide. And they showed that when you do that, you can, they proved that this code has constant distance. So up until here, it was not known how to prove that the code has constant distance. Okay, so here are the Sipser-Spielman codes. So before we talk about the factor graph, let me just describe it on the graph itself. So we start with a deregular expander graph. Okay, so lambda expander graph means that except for the top eigenvalue, all the other eigenvalues are smaller than lambda. And I'm using here lambda to be normalized between -1 and 1.
Bipartite or?
No, as you see here, it's often described as bipartite, but it's not needed. So as you see here in the picture, this is, I guess this is bipartite, but I didn't mean for it to be.
Oh, the bipartition is going to be edges to vertices.
Right, exactly. Okay, so you start with a graph and you start with the base code. Soon we'll discover some conditions we want on the base code, but for now there are none. And what we're going to do is put the bits on the edges. You see here that I put, is there a laser pointer here?
Yes.
Okay, so right, so you see that I put the bits here on the edges, and the constraints are going to be on the vertices. Each vertex will have some fixed ordering for the edges around it. It will construct a string of d bits from the bits on the edges around it, and check whether this string belongs to C0. So that's the definition of the code. You see here, we have the words are all functions from the set of edges to 0, 1. And for every vertex, V is a vertex, you look at this function only on the edges surrounding V. And implicitly, I'm assuming there is a fixed ordering here. You get a d-bit string, and this needs to be in C0. Okay. So that's the definition of the code. And you see that a different way to describe it is by using this factor graph notation. So you put a vertex here for every edge in G, a vertex here for every vertex in G. And then this vertex checks that its neighbors are in C0. So this is exactly like in the Tanner presentation. Okay, so now let's see what properties this code has. So first of all, I want to understand whether this subspace that we defined here, whether it has any code word. So what's the dimension of the subspace? And actually it's a counting argument. You say, what's the dimension? It's the ambient dimension, so the number of edges, minus the number of linear constraints. That's a lower bound, right? Because maybe all the constraints are linearly dependent, so it's much smaller. But this is a lower bound. So it's E minus, and for every vertex V, we have a bunch of constraints coming from the base code. So this is the number. You do the calculation, you get that it's exactly E times 2R0 minus 1. If R0 is bigger than half, you get the positive rate code. Okay, so that's the first condition we have on the base code. It has to have high rate, about half. Now what about the distance? So what Sipser and Spielman proved is that the distance is delta naught, the distance of the base code, times delta naught minus lambda. So if delta naught is bigger than the second largest eigenvalue of G, you get a constant distance. And the proof is really, it's really simple. Basically, I'm not going to show the proof, but think of it this way. Suppose you start with a vertex that you have some non-zero code word. Okay, you want to show that the number of 1 bits is actually a linear fraction. So you start with some vertex that touches a non-zero edge. So now the code word, the base code word that this vertex sees around it must have distance at least delta naught. So there must be some other edges that are 1s. Okay, so you have a bunch of 1s here. So now you move to the neighboring vertices, and again, they have to have a bunch of 1s around them. So you propagate and propagate. And
And it's an expander.
and it's an expander. You can use like the expander mixing lemma or the alone Chang lemma, and like 2 lines, and you get this this argument.
Why do you count ones? Or you?
If I want to prove distance,
You're taking out distance from 0 or?
yeah, if it's a linear space,
Oh, I
and I
see.
have 2 words that are close to each other, I can add them up and I get a small weight for them.
Okay.
So it's enough to show that I have all the code words that are non-zero have large weight. Thanks for the question. Okay, so these are the expander codes, and of course, the even more exciting thing that Sipser and Spielman proved is that these codes can be decoded in linear time, but that's out of the scope of this lecture. They showed an iterative decoding algorithm, which is going to be similar to what we will see towards the end of the lecture. For us, the iterative decoding will also show local testability.
But your codes will also be linearly decodable in linear time?
Yeah, because it's the same kind of thing. Yeah. Something changed. Okay, so then, of course, it's natural to ask, these are beautiful codes, right? These expander codes, are they locally testable? And in some way, they are locally testable if you know that you're given a word that's only slightly corrupt, like less than epsilon n bits have been corrupted, then it's true that the fraction of rejecting vertices is proportional to the distance from the code. But what's the issue? The issue is that it could be that once you move even further away from the code, you kind of circled back and you got to a situation where only one constraint is violated, but the word is very far from the code. So let's see this in a bit more detail. So I want to say that expander codes are not typically locally testable. They typically will have a word that's not in the code, and this word is going to be far from the code. So the distance is, I don't know, at least 1%. But only one of the vertices will even notice that there's a problem. All the vertices will think that the constraints around them are satisfied.
So if your tester was testing a random constraint, it will have very low success.
Okay, thanks. So maybe I should have started with that and said, if you think that this code is locally testable, you need to come up with an idea of how are you going to locally test it. And the only thing I can think about is to test, to select a random vertex and look around it. There's a work by Ben Sasson, Harsha, and Ashkodnikova that show that in more generality, no matter what tester you come up with, you will always fail. Okay, so let's try to see why this is true. Okay, so the first thing to notice is that if you had defined these Sipser-Spielman codes by choosing a different base code at every vertex, okay, for V naught, you chose some C naught, for V1, you chose some C1, and so on, nothing in the argument would change because all we needed is that the rate and the distance of these base codes was large. So how about this? Take this V naught and just remove one of the constraints from this base code. Okay? And all the other vertices you don't change. You get a different, at least a different definition of a subspace. And with high probability, it will actually be a bigger subspace because you removed one constraint. With high probability, it will be linearly independent of all the other constraints. So you increase the code by one dimension. What does that mean? Now take some word that was not previously in the code and now it entered the code. Because of the distance argument we had before, this word is far from everything else. So in particular, it's far from our code. But on the other hand, it only violates the constraint, the one constraint in V naught. Okay, so this is really the nightmare for local testability. It's as close as possible in terms of the constraints, but it's far in terms of having distance. Okay.
You said with high probability the dimension increases, high probability of what?
Okay, great question. So in some sense, our codes are also going to fit somewhat into this and they are locally testable. So I'm not going to prove that you can never construct a locally testable code. I mean that if you have, say, a random expander and a random C naught, everything will be linearly independent. So you're going to need, if you want to prove local testability, you're going to need to use something more about your construction. Okay, in particular, if you look into codes that we know are locally testable, like the Weizmann code, the Hadamard code, you see that the linear constraints are dependent on each other. You cannot like remove one linear constraint and the code will increase. No, you remove this linear constraint, nothing changed because you can already, it depends on some other constraint, so it's already implied. And this is what we need to construct.
So redundancy in the constraints.
Redundancy in the constraints, exactly.
So this means that the lower bound that you gave before on the dimension is actually very bad.
Right.
Did it say something about the dual code also having distance, or it's related to that somehow?
I wonder about that, but I don't know.
We don't know what the code is, so what about?
No, the fact that you can, that reducing a bunch of small constraints doesn't change the code, it means that there's something.
What does it mean about the dual code? Yeah, I think that's a great question.
What does it mean about the?
Dual code. Dual code is the code, the bunch of constraints. All the words that are inner product zero.
I don't understand. That's exactly mean that there are a lot of vectors of bounded length there, which are linearly independent of each other.
Dependent.
Which are dependent of each other. So
Right.
Yeah.
The dual code will definitely have very low weight words, right? Because these are your tests, but something else should hold there, and I'm not sure what. Okay, so now we're gonna do the whole thing one dimension up. So now we're gonna have a graph, but it's also gonna have squares. So these are these 4 cycles. And in the factor graph, we're gonna have another level. We're gonna have vertices, edges, and squares. But now if you notice here, we wrote the bits are gonna be not on the edges, they're gonna be on the squares. The constraints are gonna be on the edges, and the vertices are gonna give us dependency between the constraints, which is important for what we just discussed. So that even if I remove some constraint here, because of this dependency, it's already going to be implied by a bunch of other ones. Another way to think about it is that if one constraint is violated, because of the dependency, it forces some other constraint to be violated, and then some other constraint. So you get propagation. Okay, so now our bits of the code word are going to be placed on the squares. The constraints are going to be, an edge looks at all the squares it participates in, and yeah. Okay, so we finished with the expander codes. Now I want to talk about the graph with squares, what we are calling this left-right Cayley complex. So I'm going to start by defining it. We start with a finite group. We're going to think of a Cayley graph on this finite group. So really what we have in mind is a family of Cayley graphs. The group size is growing to infinity, but the number of generators is going to be fixed. Okay, so we have some set A of generators, so it needs to be closed under inverses. And you look at the Cayley graph of G with A. So what is this? You have a vertex for every group element, and you connect G to A times G. So if A has D elements, G has D neighbors, A1 times G, A2 times G, A3 times G. So that's the standard Cayley graph, and we're just gonna have two of them. So instead of just one set A, we're gonna have two sets A and B, and we're gonna have one set that gives me blue edges and the other set that gives me red edges. And there's a slight twist, is that with the A set, we do left multiplication, and with the B set, we do right multiplication. And why is that good? Because then it gives us these squares. You can move from G to GB and from G to AG, but then you collide. If you do the other step, you close a square. So you're going to have many, many squares in this construction. And now let's look at it a bit more closely. Okay, so the structure is this locally. You start with G, you can move either to AG or to GB. But then from both these vertices, you move to A times G times B. Okay, so you always have these squares. So every triple of group element in two generators, one from the A set and one from the B set, give you this 4-cycle. And it's really a rooted 4-cycle because it kind of singles out G as the starting point. So for this 4-cycle, there's really 4 different ways to look at it. You can start also from AG and move to AG times B, you move here, or AG times A inverse on the left, and you move here. Okay, so I wrote it out. So look at this triple. This is exactly what I said. The root is AG, and by multiplying on the left by A inverse, you go here. Multiplying on the right by B, you go here. So if you want to look at the square without the roots, you just look at all the 4 triples, you make them into one equivalence class, we denote it by these square brackets, AGB. Okay, and then you see geometrically that the square contains these edges from G to AG, from AG to AGB, and so on. And the vertices are whatever is on the figure. And the set of squares is like a set of 2-dimensional faces. All these AGB with brackets.
Just to ask, you are only taking these kind of squares. You might get something else, which is only this kind of.
Exactly, yeah, it's a good point. The graph can have other 4 cycles. We only care about these. Okay, so to summarize, we start with a finite group G and 2 sets of generators A and B. And we have this left-right Cayley complex, this object. What are the components? You have the vertices are exactly the elements of G. The edges are the edges of the 2 Cayley graphs from G to AG and from G to GB. And the squares are what we discussed. These triples where you kind of move to these equivalence classes of unrooted squares. And we're going to say that this object is a lambda expander if each one of the component Cayley graphs are lambda expander. So that's going to be enough for us.
Can I do that? One isn't, the other isn't?
You pick it to be that it is in both cases. You just choose A and B to be.
No,
It definitely could be. So you can choose a group of, or a set of generators.
it's not a group.
Bad one, and a set of generators, which is a good one. It's not a group property. That's another
It's not
paper.
a group.
Okay. Okay, and the thing is, it's already like well known for I don't know how many decades that since the LPS construction, we know of the infinite family of expander graphs with bounded set of generators. So it means that the size of A is fixed to 100, and the size of the group goes to infinity. Okay, so for example, you fix lambda to be something like 0.2. I'm thinking of lambda as normalized, so it's 0.2. So there must be some number, like I think it's roughly like 100, where you have an infinite family of expanders with that are 100 regular and have this second largest element.
A little bit trivialize this now because to say, no, not the original work about Ramanujan, but there is one more step because you got to say that the A and B should be somewhat independent. Otherwise, you can take A and B to be equal, and then this lemma is just a corollary of the old results from 30 years ago.
No, you're absolutely right. I think I have an asterisk.
Already had the Cayley expanders in the 70s. So it's even earlier, but you're right that-
No, that's not.
It's
Oh,
Because you
okay,
can have lambda as small as you want. Here, that lambda just slightly less than K.
yeah,
It's expander, but not quasi-Ramanujan. In fact,
you don't need to go there.
no, because you use Kashtan property T, but after P, you don't
No, I know, but there is Gamber and, yeah. Well, you
No,
can
okay,
get-
so there's another thing.
But your point you made, probably response.
Alex, so there is one thing is that you need lambda to be close to 0. That's one thing. Another thing is that we need some extra property here that we don't get collisions. We want that locally these squares never smush. Like it could be that from G you go to AG and from G you go to G times B, and these happen to be the same thing. AG equals G times B. Could happen. And so we need to work extra hard to find a set of generators A and B that this never happens for them. Okay. All right, I think I have it somewhere later on, but we'll see.
What do you mean by lambda goes to 0?
Uh,
Here you fixed lambda, and you're giving me an infinite sequence.
Right. So remember, even in the case of expander graphs of Sipser and Spielmann, you always needed to have lambda smaller than delta naught. Otherwise, you wouldn't get distance. Whatever, don't remember, it doesn't matter. I'm just saying, you always need to be able to choose lambda to be small enough. So also here, once someone gives me the base code with some distance, I'm going to choose lambda to be smaller than that.
And you can always do it by choosing the degree to be a little larger. You can always, square the graph, you square the degree and the lambda, square, so it goes down to 0.
No, the question goes down with what?
No, it doesn't go down. It's for any fix, but it can be arbitrarily close to 0.
Okay.
Yeah, okay. So it's 12, how long are we? Should we
Yeah.
Wrap
No,
up?
it's you have 15 minutes.
15 minutes, okay, cool, okay. Good, okay, so let's look a little bit more at the Cayley complex and then we'll define the code. Okay, so I want to look at an edge from G to AG and look at which squares touch this edge. Okay, so basically for every element B in the set of generators, capital B, I have an edge from G to GB and also from AG to G to AGB. Here I have AG times B1 and G times B1, AG times B2 and G times B2. Right, so basically I have like a little book here where this edge is the spine and all these are pages, all these squares. So for every element in B, I have one page in this little book. Okay, so what I mean to say here is that I have a natural bijection between capital B and the set of squares touching an A edge. And symmetrically, if you start with a B edge from G to G times B, then you look at all the A elements in capital A, and you get a similar thing. You get a bijection between the set of capital A to all the squares that touch this edge. Now let's look at what this complex looks like from the perspective of one vertex. Okay, so I fix a vertex G. So firstly, I see that I have A neighbors and B neighbors, right? So these are the A neighbors and these are the B neighbors. Now for every choice of neighbor in the A set and neighbor in the B set, I can complete the square like this. Right? So I'm going to have a square for every A and every B. And notice also that if I choose some fixed A neighbor, like let's say from G to this guy, A times G, now I look at this as like a spine of a book, and who are the pages? It's this, and this, and this, right? So I have here like a little book on the A1 edge, and I have another book on the A2 edge. So really what you see here is that the squares around G are organized in like an A times B little matrix.
Or the antipodes of G in the square.
Right, all these, actually the big blue dot, the black dots are the neighbors, and the smaller black dots are not neighbors of G, they're distance 2 away from G, right? And they are the antipodes of these squares. Okay, and I guess you see here that I wrote that there's a bijection between the pairs AB and the squares AGB. This is only going to be a bijection if we have this property that we were talking about earlier with Alex, that you never have a collision between A times G and G times B. So it makes the whole thing much more regular and much easier to analyze. So I guess I want to say here that this is the source of this image. So the squares of the complex, you can move from one square to another square on each one of the spines of the square, and you can move to many different locations. Okay, so we're finished describing the Cayley complex. You can see that I think it's a quite simple object. It's not very fancy. Maybe we were a bit disappointed because we thought we will need some more fancy high-dimensional expanders for this.
What do you mean a bit?
Very disappointed. Okay. So let's define the code. Okay, so we're going to fix, just like in the Sipser-Spielmann situation, we're going to fix a base code. But now we have two kinds of edges. So let's fix a base code CA to be some subspace of 0, 1 to the A, and CB to be some subspace of 0, 1 to the B. Of course, if A and B have the same size, you can just choose one base code. It's not a problem. And you're going to define the code by putting now the bits on the squares. So code words are functions from the squares 2, 0, and 1. You just label each square by a bit. And what are the constraints? Every edge looks at the book around this edge and it has a natural bijection between this book and either the set A or the set B. So it wants these bits to be in either CA or CB, depending on where we are. That's it, that's the code. So you can write it here. We have all the functions from squares to 0, 1. And for every choice of A, G, and B, when you fix G and B, so you're fixing an edge from between G and GB. And then when you range A over all the possible elements of capital A, you want this to be CA. And similarly for edges of the A type. So that's your code. Now you need to start finding out what are the properties of this thing.
Every bit is in 4 constraints.
Every bit is in 4 families of constraints. So for example, this is a constraint that says you need to be in CA. So maybe there's more than one constraint in there, but yeah. Okay. I guess if you think of the factor graph of the 10, so this code is a 10 code. You can put the squares on one side, the edges on the other side, and each edge wants the local view to be in C0. So every square participates in 4 different edges.
But every bit is in a constant number of equations.
Yes.
The total number of equations is linear.
Yeah. And we're going to use this to show that this code has rate. So, yeah. So how are we going to prove that this code has rate? We're going to calculate the dimension just like we did before. We're going to say the ambient dimension is the number of squares. So that's actually, what's the number of squares? It's the number of triples, A times B times G, divided by 4, because every square appeared 4 times. So that's the number of squares. And the number of constraints, you count it, and I'm not hiding anything. It just comes out to be this. It's a very simple calculation. Okay, and the distance also is very straightforward, very similar to the Sitzer-Spielmann situation. You get that the distance is delta naught squared times delta naught minus lambda. So here you already get 2 constraints on the base code. One is that R naught needs to be high enough for this to be non-zero. Okay, so I guess it needs to be at least 3/4 for this to be positive. And delta naught needs to be at least bigger than lambda. Okay, so this is very similar to the situation we had previously.
Is this like supposed to be the second Betty number or something like that of the Q complex?
I don't think so.
We don't know. It's everything just one. It's a good question, but
Can you
so
repeat the
brand new,
question,
we don't
please?
know.
Is this the second Betty number? So the dimension of the second cohomology?
So at some point, we wanted to give it some interpretation of cohomology, etc., but eventually we changed the code and now we don't know, but hopefully in the future we will understand.
Actually, for Sitzer-Spielmann code, so Roy Meshulam had a nice description of them as cohomologies of something. Very possibly you can do that here.
Should be also
right?
use some.
But we don't know.
So the test is the natural test? That you
Yeah, so what would be?
an edge.
Yeah, that's a natural test. It's easier for us to analyze a less efficient test, which is pick a vertex and check that everything around it works out. So let's talk about what's going on around the vertex, actually. So in the Sitzer-Spielmann code, we had 2 levels. We had locally, you had to be in C0, and then globally, there was the code. Here we have another level. So locally around an edge, you need to be in C0. Then there's also something going on around the vertex. We'll talk about it soon. And then there's a global code. So there's an intermediate code here whose local testability is going to help us prove local testability globally.
Do we really have to check? I mean, it's just for the computation of the constant that we have to check the vertices. I mean, one can really present the test.
What's the access? Absolutely. Yes.
Just like
Yeah.
not so clear what's optimization of constant.
Yeah, I definitely think the analysis can be improved. We just proved that some constant works, but yeah, it's not optimal. I don't think it's optimal. Okay, so I want to talk about this intermediate code around the vertex. I want to show that this intermediate code is a tensor code. Okay, so I just copied the definition of the code down here. Let's look. So what is my claim here? And choose some code word, some F in the code. So it's a function on the squares. And I'm going to fix a vertex G. And I'm going to look at the restriction of the function to all the squares that touch G. Okay, so I'm writing it like this. And the claim is that it belongs to this thing. This is the notation for the tensor code CA tensor CB. What this means is just a collection of matrices whose rows are in CB and columns are in CA. Okay, so it's a linear subspace. It's called the tensor of CA times CB. And it should be clear from the definition, right? Because since you're in the code, for every fixed A, see here, for every fixed A and G, when you range B, you need to be in CB. So that exactly tells me that for every fixed row, you need to be in CB. And for every fixed column, G and B, the column needs to be in CA. That's exactly this constraint. Okay, so it's immediate. Remember we said that the squares around the vertex line up to be this matrix, and it's immediate just from the definition that all the columns need to be in CA and all the rows need to be in CB. Immediately you get that the intermediate local view of the code is a tensor code. Okay, so the theorem is that if this square complex is a lambda expander, and we need some condition on this local tensor code, we can't take just any CA-CB. We want that CA tensor CB has some local testability property. Talk about it tomorrow. So and then we need some condition relating lambda to delta naught and to the local testability of the tensor code. But remember, we said that we can choose lambda to be arbitrarily small. So we first fix the base code, we get delta naught in row, and then we take lambda to be small. Okay, if all of these conditions are satisfied, then the thing is locally testable. Okay.
Irit, you mean CA tensor CB is robustly testable via the natural tester? Or
Of the random row, random column. Thanks. Yeah, that's true. Okay, so what's going to be the tester? This is what Zev was asking. The tester is going to be select a random vertex, read all of the squares, all of the A times B squares touching it, and check that this thing is in the tensor code CACB and accept if so. Okay, and what you need to prove is that the fraction of vertices in which what you see is not in the tensor code is lower bounded by the distance. So if you have a word that's far from the code, many of the local views are going to reject. You cannot have what we constructed, this counter example we did with the expander codes, where everything looks great except in one V naught. And how come? What changed? What happened here that didn't happen there? See here that all the base codes necessarily had to be the same CA and CB. We can't have different CA in different locations. And there's a lot of dependencies between the constraints. So we'll see it more tomorrow. Okay. I'm gonna skip this. This is talking about what it means exactly to be locally testable for the tensor code. Talk about it tomorrow. Let me just give you one slide of how you would prove local testability. It's really through this algorithm, this iterative self-correction, just like Sipser and Spielman. How would you do it? To prove local testability, you're thinking, okay, start with some function f. I don't know how far it is from the code. Maybe it's in the code. I don't know. And I'm going to slowly try to fix it to be in the code. And I'm going to hope that the number of steps I take to fix it is related to how many constraints are unhappy, how many local views are rejected. Okay, so this is the algorithm. First, for every local view, you correct the local view, you get a bunch of local views that maybe are inconsistent, and then you measure your progress by every time two local views are inconsistent, you add one to your, so you define this progress measure to be how many inconsistent pairs. And then locally, you look at the vertex, it looks at all of its neighbors, some of them are inconsistent, some of them are consistent, and it changes its value to be more consistent with its neighbors.
So just a second, just to clarify, you are going to prove that the tester works, so you want to prove that if a word is far from the code, it rejects it with high probability.
Right.
This is going the other way, say if the rejection probability was too small, you'll prove that this word actually is close to the code.
Right.
So that's what this process
Right.
is doing.
Right. Actually, maybe. Okay. Actually, let me define the algorithm first, and we say again what Avi said. So start by every vertex kind of collecting the best local view. So a vertex might look around, see something that's not in the tensor code. Okay, so it's going to choose some local view that's as close as possible. And then we set this loop where every vertex tries to change its local view to be more consistent with its neighbors until no vertex can do any more improvement. And then that's the end of the algorithm. Now, two options can happen. Either there is no more inconsistency, then we're happy, we can output whatever we see and it's going to be a code word. Or there is some inconsistency and then we output the stuck. And what we're going to prove is that the number of steps, if we reached 0, the number of steps we took is proportional to the distance. And if we got stuck, it means that there was a lot of rejection to begin with. In other words, if there was only a few bad local views, you're not going to get stuck. What?
What makes you stuck?
Stuck is you're keeping track of different local views at different vertices. They don't have to be consistent. And every time you're trying, a vertex is trying to change its local view to be more consistent with its neighbors. Could be that there's no better situation. You're inconsistent and there's nothing you can do. And you're stuck. And what we're going to prove is that if you're stuck, it must be that there's a lot of inconsistency, meaning that the tester rejected with high probability.
It's like you did a gradient descent, but you got into a local minima, which doesn't give you as low as you want.
Exactly. Right. So what you're really showing is that in this situation, it's a kind of situation where there's no local minimum, except for 0, except for the global minimum. Okay, so the two things you need to show is that the number of steps of this loop is proportional to the rejection. And okay, I guess I said these things. So let me just skip this because I'm running out of time and I'm going to do this.
That's okay, don't.
I mean, I'm going to do this in more details tomorrow. So just wanted to say how to instantiate the code. Okay, so the proof of local testability I want to do tomorrow carefully and slowly. It's not going to be super difficult, but it will show how the expansion of the graph kind of makes these rejection things propagate. Suppose we are happy with that. Then I want to just summarize and say, how are we going to get a family of error correcting codes with constant rate, distance, and locality? We start with some rate R. We take a family of base codes with rates that's sufficiently large, just inverting the formula. And then we take lambda to be small enough with respect to both delta and rho, like we showed before. And this gives me some constant D, which is the size of this set of generators A and B. So even though A and B formally, they are different for different ends, their size is always going to be at most, 1 over lambda squared, roughly, like we say here. And right, and then our code is just going to be this family where the group goes to infinity. A and B are going to stay of fixed size, and the base code is some fixed base code of length D from this family.
Is it important that D is 1 over lambda squared?
No, it just needs to be able to be small enough. Yeah, that's true. You need to be able to say for any small epsilon, there is some D.
Yeah, but that's, you can always say. Take any expander and raise it to a power.
That's right.
Or even in Cayley graphs, it works.
Right, that's true.
So you don't.
Okay. The robustness rho is of the tensor code CD times CD, right?
Right. So really there's 3 parameters, right? There's distance, rate, and local testability. And each one of them is some kind of constraint on the base code. Distance and rate is just like an expander code, and the rho is some constraint on the tensor code. And tomorrow, hopefully I'll be able to go into more details about that. Yeah.
So the number of constraints to define the code has to be less than the number of bits, right? So the number of edges is less than the number of squares.
Right.
And to test, you only choose from those constraints. I thought that somehow for LTCs, you needed more like a lot more constraints than bits or something. Wasn't there some?
Yeah, but look at the intermediate code, the tensor code. A tensor code already has redundancy, right? Because
Okay, so this.
you know that all the columns.
There that makes it a lot more constraints than. Oh, okay.
It's a constant more, but
It's a big constant.
not. Yeah, I think probably we wouldn't have thought that this should work, right? But yeah. Okay, so yeah. Okay, I want to talk a little bit about high-dimensional expansion, but now I'm getting out of time. So this idea of using this high-dimensional expansion was already around. A lot of people were thinking about it. And you see here also there's this local to global. You prove something on your local code and use the expansion to show that it lifts to the global thing. This goes all the way back to Garland that used this to prove the vanishing of cohomology. And then I said that there were various works that use this local to global also for random walks, for systolic expansion, topological overlapping. With Harsha, Dickstein, and I guess it's not here. Maybe it's in the next, yeah. With Dickstein, Harsha, and Lonsby, we showed that actually, if you have a high-dimensional expansion and locally you're locally testable, then you get a global locally testable code. But the problem is we didn't know how to instantiate this. And yeah, so it looked like a void idea. But okay, in this work, we worked a lot of different directions trying to find an instantiation. Maybe Alex will talk about it, that we were really trying to work on this complex using very interesting ideas, but somehow this sidestepped this whole issue with these simple Cayley complexes. Okay, there's a lot of questions left. Firstly, can you construct locally testable codes on these other complexes, and what does that mean? And what do these objects look like? The Cayley complex is a very two-dimensional thing. Can you get a three-dimensional, like a cubical complex? That looks like an interesting question. And of course, also LTCs came about through PCPs, and it would be awesome to get a PCP using similar ideas, but no idea about that. Okay.
Thank you.
Questions? You said it after the algorithm, your remark on Avi's remark.
Which was?
Why the negation is proving what you want.
No, it's, yeah, but she'll do the analysis. She will do the analysis of the testing, local testing.
It's like a contrapositive.
Yeah, it's just the same.
Irit, so it seems like
Can you
the
say
code is binary.
what groups to use?
Like the LPS generator, so it's 2 by 2 matrices over some finite field that goes to infinity.
You don't need the LPS generators. Sorry, Alex. I'm just saying you take any.
No. But we want this no.
I know, yeah. So you need two.
No, but that just means that you have no conjugate.
So if you take A to be elements of order two,
I know.
B to be elements of order higher than
It's a condition that is unrelated to Ramanujan.
That's all.
That's all I'm saying.
Yeah.
It's not
unrelated to Ramanujan.
There's a conjugation condition that's not related.
But for example, if you take A to be elements of order 2 and B elements of order not 2, they're never going to be conjugates.
We know from Bourgain-Gamble, for example, that SL2P is expanding with any pair of generators.
No, there is something you let me stress, because that's actually related to the seminar we are running this year.
Okay.
On arithmetic group, you see what happened. We know that if we have a mother arithmetic group, then basically you can choose whatever you want, and you get downstairs and you get expanders. And okay, maybe you can get. I mean, you have to be careful because you need more than expander. You need like very small eigenvalue, and that's Gamble Bourgain don't give you.
No, he's taking powers. He's taking powers.
Okay.
But now, even if the elements upstairs are not conjugate to each other, they can be downstairs conjugate for all P. That's kind of a local, there is no local to global property here, this one. And that's actually the kind of thing that we are talking about in the seminar. And so you really, we had a difficulty. I mean, maybe there is a simple argument, but somehow we use a little bit, a very special case that we could prove it. Maybe there is a more robust way to do it. We are using a very particular Ramanujan complex somehow to do it. But maybe there is.
But it's a conjugation condition. It's not a Ramanujan eigenvalue.
To be honest, we are even not sure that this conjugation condition is really so much necessary. But you know, all this was done in the last few weeks, basically. And so we are still.
More questions? Audience in Zoom.
Yes, so it seems
All right,
that.
thank you very much.